Hello everyone, welcome to today's lecture. Today we're going to be talking about a new parallel pattern, which is prefix sum, or which is also called scan. This lecture is going to be in two parts. So today we're going to do part one of this lecture, this chapter, and then next lecture we're going to do part two of the chapter. Okay. Before that, let me quickly summarize what we covered last time. So last time we spoke about reduction. We said that reduction is an operation that reduces a data set into some kind of summary. Common reduction operations include sum, product, minimum, maximum, etc. And we focused on the sum reduction operation. And we said that the reduction operation has to be associative, commutative, and have some kind of well-defined value. We started by a very bad implementation of reduction, and this implementation was based on atomic operations where every thread would access one element from memory and use an atomic operation to accumulate that value to a global sum. And we said that this is a very bad implementation because what actually happens is the hardware ends up serializing all of these atomic operations. So it's not a very good idea. So instead, we said what we can do is we can do a parallel reduction where we have this kind of tree. We have this kind of tree reduction strategy where we do multiple iterations, and in each iteration, we launch half as many threads as we have elements, and each thread is going to add two elements and produce one element. And by doing this, every iteration, the number of elements that we have is going to be divided in two, and we keep iterating for log n number of times until we get until we get to the final result. And we said this pattern is called a reduction tree. Now, because this pattern requires synchronization across each one of these steps, the way that we actually implement it in practice is we have this kind of segmented reduction where we divide our inputs into segments, and each thread block takes one of these segments. The thread block uses the reduction tree strategy to reduce that segment, and then each thread block, one thread in that thread block will use an atomic operation to accumulate the reduced value of the block segment to the final accumulator. So having said that, we then proceeded to implement a reduction tree inside of each thread block. Our first strategy was this, where we assigned a thread to every other element in the segment, and that thread would reduce the element that would add that element to the element that's right next to it, and on the next iteration, every other thread drops out, and the stride becomes 2, and every thread adds a value to the elements that are 2 strides apart, and every iteration, half the threads drop out, and the stride doubles until we get to the final value. So we implemented this, but we said that this particular approach is not very efficient. And the reason it's not very efficient is because when every other thread in each warp drops out, what happens is that all the warps remain active, but each warp has 50% SIMD efficiency. And on the next iteration, 25% SIMD efficiency. In the next iteration, 1/8, etc. And then the warps start dropping out towards the end, but the warps that are active have only one out of the 32 threads that are actually working. And we said this is very bad for control divergence. We also said that this pattern is not very good for memory coalescing because the threads that are active are not accessing elements that are adjacent to each other in memory. So what we did to avoid these two problems is we changed the way that we are arranging the threads, assigning the threads to data, where the threads are assigned to contiguous data elements. And that way, when they access the data from memory, the accesses are coalesced. And also, when the threads drop out, they drop out from the end. So in the first iteration, all the threads are active. In the next iteration, the top half of the threads are active, and the bottom half drop out, and the bottom half of the threads remain active. In the next iteration, again, the top half drop out, and the bottom half remain active. And the advantage of this is that rather than having some of the threads in each warp drop out, we have entire warps drop out of the computation so that we always have all the threads in the warp active or all the threads in the warp not active, until, of course, we reach a situation where we have a single warp working, in which case that control divergence is inevitable. Another optimization we applied is using shared memory. So we said that once we load the data from global memory, we can put it in shared memory and execute the reduction tree inside of shared memory. And then yet another optimization we applied is we observed that this pattern here involves frequent accesses to shared memory. It also involves frequent barrier synchronizations. And the way that we can reduce that is instead, when the threads come down to the final warp, it's because the threads in the same warp execute in lockstep, they have a special relationship where they can synchronize and share data faster than using shared memory and sync threads. And they can do that with something called the warp level primitive, particularly the warp shuffle functions. So a warp shuffle function is a function that allows threads that are in the same warp to share data between each other's registers without having to go through shared memory. And they also don't have to use sync threads. The shuffle function has kind of an implicit synchronization in between the threads. So we use this warp shuffle function so that when we get to the final warp, instead of having to use shared memory and sync threads for every iteration, we instead use the shuffle function in order for us to reduce how much sync threads and how much shared memory accesses we make. We also said that we can use cooperative groups instead of warp shuffle functions. The cooperative groups API is a higher level API. It generates shuffle functions underneath, but it's kind of a friendlier API whenever you want to do warp level programming. We didn't actually implement this in class, but you can do it in the assignment if you want. It's kind of a nicer API than the low-level shuffle instructions. We then said that we got rid of the synchronization in the last warp, but in the earlier warps, we still have synchronization every step. And the way that we can get rid of those is by doing a two-stage warp shuffle approach, where instead of using sync threads and shared memory to do the first half of the reduction tree, we can instead have each warp do its own reduction at the warp level, and then we rearrange the data, and we have the one warp do the final reductions. And the disadvantage here is that now we have more control divergence across the warps in the first few phases. However, we got rid of the sync threads and we got rid of the shared memory accesses, which overall gives us a net benefit. Finally, we looked at thread coarsening, and we said that the cost of parallelization and reduction is the fact that you have to do all the synchronization, the fact that you have this control divergence that you have to tolerate. And if the blocks actually run in parallel, that's good. But if the blocks don't run in parallel, then that's a waste. And what we can instead do is we can do a sequential reduction in each thread and then do a parallel reduction across the threads. And the sequential reduction obviously doesn't have any pair synchronizations, and it doesn't use any shared memory accesses. So this would look like this. If we had two thread blocks and they were serialized, then you would have this phase where you're doing the reduction and the hardware is underutilized, and you're using sync threads, you're using shared memory. And then you would have the next thread block would come in, and you would have this phase where the hardware is underutilized again. But if the same data is reduced by one thread block where thread coarsening is applied so that each thread sequentially reduces 4 elements before we start the reduction tree, then in this case, we replaced these two reduction tree phases where the hardware is underutilized with a phase where the hardware is fully utilized, and then later only one reduction tree phase where the hardware is underutilized. So this is what we covered last time. Does anybody have any questions about what we covered last time before we talk about scan? All clear? So you have an assignment due next week in which you will be implementing this reduction, but there are some modifications that we made in order for it to be kind of different from the code that we implemented in class. Okay, so then let's get started and let's talk today about prefix sum or scan. So what is scan? A scan operation is an operation that takes an input array, so x0 to xn minus 1. It takes an associative operator. This could be something like sum. Again, it could be product, it could be min, it could be max, etc. And then the operation returns another array. So this time, unlike reduction, where we return just a single value that summarizes the array, in scan, we return another array, y0 to yn minus 1, where every element in that array is going to be the result of applying the operator to the preceding elements and maybe the corresponding element. In the inclusive scan, we're going to apply the operator to the corresponding element and the preceding elements. And then in exclusive scan, we apply the operator only to the preceding elements, right? So here, yi or y1 is going to be in inclusive scan will be the operator applied to x0 and x1. And then in exclusive scan, it's going to be the operator only applied to x0. In general, yi will be the operator applied to x0 up until xi if it's inclusive, and x0 up until xi minus 1 if it's exclusive. Is that clear? Let's do an example. So for
Professor,
example, yes.
uh, in an exclusive scan at y0, it's not going to be defined.
So y0 in exclusive scan will be the operator applied to the preceding elements, which are nothing. So when you apply the operator to nothing, what do you get?
So it's like the identity of the
It'll be
operator.
the identity, exactly. The sum of an empty array is zero. So in
Okay.
general, the operator applied to the empty array is going to be the identity, exactly.
Okay.
So we'll see that in an example. So here, an example where we have addition. If I have this array 3, 6, 7, 4, 8, 2, 1, 9, and I apply the inclusive scan, over here, the first element is going to be 3, which is the sum of 3. The second element is going to be 9, which is the sum of 3 and 6. The third element is 16, which is the sum of 3, 6, 7, etc. The last element is 40, which is going to be the sum, which is the sum of all the elements in the input array. In the exclusive scan, the first element is going to be 0, which is the identity. That's the sum of the preceding elements, which in this case are nothing. The second element is going to be 3, which is the sum of the preceding elements, in this case 3. The third element is going to be 9, which is the sum of 3 and 6. The fourth is going to be 16, which is the sum of 3, 6, and 7, etc. And the last element is going to be the sum of everything except the last output element is going to be the sum of everything except the last input element. And as you can see here, the exclusive scan is basically just the inclusive scan, but all the elements are shifted by 1. We drop the last element and we include the first element, which is the identity. So in general, if I have an array x0 to x7, in inclusive scan, the first element is the operator on x0, the second element is the operator on x0 to x1, the third element is the operator, element 2 is the operator on x0 to x2, etc. And in the inclusive scan, well, the first element is the identity, the second element is the operator on x0, the third element is the operator on x0 to x1, etc. And the last element is the operator on everything except the last input element. Okay, so this is what scan does. Is this clear? Any questions? Okay, so if I were to implement scan sequentially, what would I do?
Previous output plus the current input.
Right, exactly. I would iterate through this array, and in each iteration, I would take the previous output element, add it to the current input element, or apply the operator to the current input element to get the new output element. Exactly. So the code for that would look like this. So for inclusive scan, I'd initialize output of 0 to input of 0. And then in each iteration, the new output is going to be the old output plus the new input element. In exclusive scan, I would initialize the output to 0 as opposed to input of 0. And then in each iteration, the new output is going to be the old output plus the old input element, not the new input element. Okay? And we can generalize this to where here we use the identity, and here we use some function which represents the operator instead of doing just addition. Okay? Okay, great. So next we want to talk about how to parallelize scan. Okay, but before we parallelize scan, I just want to point something out. So when we parallelize scan, we're going to have to do some kind of synchronization across the different workers. So similar to reduction, what we're going to do is we're going to do a segmented scan. And in a segmented scan, what we do is we divide our input into segments. Every thread block is going to scan a segment of the input. And then we're going to have to do some kind of synchronization across thread blocks in order to combine the scan segments of each thread block into a globally scanned segment across all the blocks. All right. So for now, what I'm going to do for today's lecture, I'm going to do is I'm going to focus on implementing parallel scan inside of a single thread block. Okay. And we're going to look next time on how we're going to combine. Well, we're going to do other things next time, but the second half of the next lecture, we're going to look at how we're going to combine multiple segments across thread blocks into a single, excuse me, into a single scan thread block. Is that clear? So what we're going to do is the following. We're going to take our input segment. We're going to partition it across thread blocks. Every thread block is going to scan its input segment into a scan segment, right? And then later on, we're going to worry about how we're going to combine these scan segments into one kind of globally scanned segment across the entire grid, okay? But the focus of today, or the beginning of this lecture, is going to be just having one thread block scan a segment of the input. Somebody had their hand up. Do you have a question?
Yes, so the outputs are not going to be correct if we look at the individual blocks, right?
Yes, that's right. Because later on, so this thread block, when you scan the segment inside of the thread block, later on you have to correct that by adding also the sum of the previous elements before the thread block.
Okay.
So
Right,
then
so
it turns
that's
into a reduction problem.
it's actually another scan problem, or it could be a reduction problem. We'll see. So let's kind of let's wait, hold on this, and we'll see there are different ways of doing this, and we'll talk about the trade-offs between these different approaches. But for now, what we're going to focus on is doing a scan inside of a single thread block for that block segment. Is that clear? Okay, so how do you suppose we should do this, right? If I want to scan this input array in parallel, what ideas do you have?
We can take all of the input and just put all of the output, but so we'll have to have a very small input. Each thread will have to do a lot of work.
So I'm sorry, I didn't fully understand. I didn't fully understand that.
So
yes, go
if we
ahead.
have all of the inputs,
Mhm.
we can just do the first operation and place the first output. Do another operation, place the second output. Another operation, third output.
But that's sequential, right? How would you do it in parallel?
Could we assign a thread to each output?
Okay, so we could assign a thread to each output. How would the thread do the scan?
I think we need to make use of the same values. For example, both x2 and x3 can use the summation of x0 and x1. So we need to make sure for all threads to have similar, so making use of similar computations.
Okay. Okay, yes, so that's a good insight. So a very trivial way to do it is you can assign a thread to each output element, and that thread could do a sequential scan of the input, right? But that's not really very helpful, because the last thread is going to do a sequential sum of the entire input array, which is the same amount of work that you need to do a sequential scan. Okay? So if I have every thread do a sequential scan, that won't work. But what somebody correctly observed is that there is some reuse. So here, if I want to get the scan of x3, I can somehow reuse the result of the thread 1, which is going to be scanning x0 and x1, or maybe thread 2, which is scanning x0, x1, and x2. Okay? And this kind of feels like a reduction, right? And indeed, scan is very related to reduction. And to show you that, let me kind of show you a reduction and see how one reduction interacts with the results that we want for scan. So let's say I do a reduction, and this time I'm going to do the reduction where I assign threads to elements, and each thread is going to get the value to its left as opposed to add values from its right. So let's say we do a reduction tree on this array right here. So in the first iteration, every element is added to an element that is 1 to its left. Okay. Next iteration, every element is added to an element that is 2 to its left. And next iteration, every element is added to an element that is 3 to its left. One thing you'll notice is that after doing one reduction tree, I already have the values that I need for some of the output elements, right? So I have the sum of x0 to x7, which is the value that I need at the end of the array. But I also have the values of the sum of x0 to x3. And I also have the sum of x0 to x1 in this position. So doing one reduction tree to get the very last element also gives me as a byproduct the results of all these other elements. Element 0, element 1, element 3, and of course the final result, element 7. Is this clear? So a parallel reduction tree for the last element gives us some of the other elements as a byproduct. So what elements am I still missing? Well, I'm missing element 6, for example. Okay, here element 6, I don't have anything for it. So what I could do is I could also do a reduction tree for element 6. So if I do a reduction tree for element 6, that's going to look like this, right? This is my reduction tree. Of course, it's not a full tree here because here I would go out of bounds. But one thing you'll notice is that when I do a reduction tree for element 6, I also get the value for this element over here, x0 to x2, as a byproduct. So now when I did a reduction tree for element 6, I'm also getting the result at element 2. So now I'm still missing elements, the elements at 4 and 5, positions 4 and 5. I could do a reduction tree for the element at position 5, and I could also do another reduction tree for the elements at position 4. Okay, so I can do the scan operation by doing a bunch of reduction trees, and I don't need to do a reduction tree for all the elements in my output array because I already get the values of some of the outputs as a byproduct of these reduction trees on the other inputs. And as a matter of fact, I don't have to do all these reductions one after the other. I don't have to do a reduction tree for element 7, and then a reduction tree for element 6, and then a reduction tree for element 5, and then a reduction tree for element 4. What I could do is I could do these reduction trees all in parallel with each other. Okay? Or I could, in other words, I can overlay these 4 reduction trees that I just showed you with each other, and the overlay of these reduction trees will look something like this. And one thing you notice is that there is an overlap in the branches of these reduction trees. Let me go back and show you that. So here, you'll notice that the first reduction tree adds elements 0 and 1 together. It also adds elements 2 and 3 together. The next one doesn't, but the third reduction tree also adds elements 0 and 1 together, and also adds elements 2 and 3 together. So the second reduction tree over here adds elements 3 and 4 together. It adds elements 5 and 6 together. It adds elements 1 and 2 together. And then the one that comes later, this fourth reduction tree, also adds elements 1 and 2 together, and it also adds elements 3 and 4 together. So these reduction trees are not completely mutually exclusive. They have overlapping branches. And that's why when we overlay these reduction trees together, we kind of, these branches kind of, get fused into just a single operation. So the overlay of these reduction trees looks like this. What we do is on the first iteration, for every element, we add the element that is 1 to its left. On the next iteration, we add the element that is 2 to its left. On the next iteration, we add the element that is 4 to its left, etc., until we get the final scanned output. And this is how we can do a parallel scan by doing a bunch of parallel reduction trees overlaid with each other. Is this clear? Any questions? I saw some hands go up. Hopefully I answered your question while explaining, but if not, please go ahead and ask.
Doctor, but isn't this worse than sequential right now?
What do you mean it's worse than sequential? In what way is it worse than sequential?
In sequential, we only have to do the top part.
So in a
Right.
sequential scan, we have to do 7 steps, right? 1, 2,
Yes.
we have to do 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. Over here, these are being done in parallel. So how many steps do we have? We have 1, 2,
Also have
3
three
steps,
steps. Okay.
which is log of the number, which is log of the size of the input.
Because
But
the
you're
steps
right,
are being
but you're right
parallel.
in that what we are doing is we're doing more additions overall, right? So in a sequential scan, we do 8 additions, correct? Or 7 additions. In a parallel scan, we're doing 7 additions in the first iteration. We're doing 6 in the second or 6 in the second iteration, and then we're doing 4 in the third iteration. So we are doing more additions overall. But because we're doing them in parallel, we are executing fewer steps overall. And this is a point that I'm going to revisit next time. This idea of a parallel algorithm doing more work than a sequential algorithm is called work efficiency. And we haven't seen it yet. So far, all the parallelizations we've done, the amount of work done by the parallel algorithm is the same as the amount of work done by the sequential algorithm. Here, this is no longer the case. And we are going to visit this point of work efficiency kind of later on. So hold that thought. But if we assume that all this work is done in parallel, we've reduced the number of steps that we need to do the scan from 8 steps to 3 steps, or in general, from n steps to log n steps. Okay, clear? Other questions? Okay, so to do this in parallel, what we can do is we can assign a thread for each element in the input segment, and that thread can be responsible for adding that element to the element that is stride to its left inside of each iteration. Clear? Okay. And one optimization that I'm going to apply, I'm just to kind of save time, I'm not going to do this and then do that optimization. One obvious optimization that we can apply, and somebody already mentioned this in the chat, is what we can do is we can move our input segment into the shared memory, and then we can do we can do all of this in the shared memory, and then we can put the final result back into the global memory. And one thing I didn't mention is this scan has multiple names. One of the names is a Koji-Stone parallel scan because it's inspired by the Koji-Stone hardware adder. So we kind of call it Koji-Stone parallel scan in the book. It also has other names in the literature, so you might come across it with other names. Okay, great. So we said that we're going to load our input segment into shared memory. We're going to do this pattern right here, and then we're going to put the final result in the global memory. Let's move to the terminal and let's implement this parallel scan. So I'm going to go here. I'm going to open my code. Here I've implemented, I have a kernel that takes an input array. It produces an output array. N is the size of the array. And then also we have a partial sums array. The partial sums array is basically an array where every thread block is going to put its final sum, and this is going to be used to combine the scanned value across all the different, it is to combine the values across all the different blocks. You don't have to worry about this. We're going to implement it, but you don't have to worry about this today. Later on, I'm going to talk about, how I'm combining all these values across the blocks, okay? So when we launch this kernel, we're going to launch it with as many threads as the input segment. So the block dimension is going to be 1024, and also every input is going to take every thread block is going to take an input segment of size 1024. Okay, so let's get started by implementing this kernel. So first, every thread is going to identify the element that it's responsible for. We're used to this now. Unsigned int I is equal to blockindex.x times blockindex plus threadindex.x. After that, every thread, we said we're going to load the input segment in shared memory. So every thread is going to load the value from input of I into a buffer at its corresponding thread index. So we're going to declare a buffer in shared memory. Let's just call that buffer underscore S. The size of the buffer is going to be the block dimension. Every thread has an element, and every thread is going to load a value into that buffer corresponding to its thread index from the input buffer. Okay, so every thread gets the value from input of I corresponding to its global thread index and puts it in the buffer at a location corresponding to its thread index within the block. After I do that, after the threads load this input buffer to shared memory, we have to sync threads because the threads need to wait for each other to finish loading before they start computing, because this thread is going to need the values, the input value for that it loaded, but it also needs the input value that another thread loaded. So we're going to have a sync threads over here before we start with our parallel scan implementation. Okay, great. So now we have our input
Professor,
segment.
there's a typo.
Yes, thank you.
Professor?
Yes.
So regarding the thread index, do we need to check boundary in case it's less than n?
So yes, you're right. We have to do boundary checks, but as I've been doing in the course, I will not do the boundary checks in class. I will leave those for you to do inside of the assignment.
Oh,
Okay?
okay.
So in class, just so that we can go quickly and also to leave some challenge for you for the assignment, I'm going to not worry about the boundary checks. I've already made sure that n here is a multiple of 1024. But of course, in the assignment, you're going to have to worry about making sure that you get all the boundary checks correctly and you can load zeros when things are out of bounds.
Sure.
Okay?
Professor, هون مش we need a boundary check to check that if the thread is greater than 0, the thread index. When we start
When we start, yeah, we haven't started yet. Yeah, when we start, we're gonna have to make those checks. You're right. So let's hold that thought until we actually get started. Okay, so now that we have our input and shared memory, we have to iterate. Okay, and we have to do our every thread has to do its addition. So how to iterate? Well, we'll see in the first iteration the stride is 1, second iteration the stride is 2, third iteration the stride is 4. So basically we iterate from stride 1 until the stride is the size of the input segment divided by 2. In this case, the size of the input segment is also the block dimension. So we're going to iterate, we're going to do 4 unsigned in stride. The stride starts at 1. It iterates until we get to block dim over 2, right? Because in this case, our block dimension is 8, so our last stride is going to be 4, which is 8 over 2. And in each iteration, we're going to multiply the stride by 2. Okay? Now, what do we do in each iteration? So in each iteration, every thread is going to go and it's going to add its element to the element that is stride to its left. Okay, so we're going to do buffer underscore s of thread index dot x is equal to buffer underscore s of thread index dot x plus buffer underscore s of thread index dot x minus stride. Okay, so every thread adds the value in its buffer, the value at its position in the buffer to the value that is stride to its left. Okay, and that's what's happening here. Now, one thing to note is that not in every iteration, not all the threads are active. In particular, when the stride is 1, the thread 0 is not active. Why? Because stride 1 is out of bounds. The element that's 1 to its left is out of bounds. When the stride is 2, threads 0 and 1 are not active because the element that is 2 to their left is out of bounds. When the stride is 4, elements 0.
So we just have to check that I is greater than the stride.
Right, exactly. So the check that we have to make sure to deactivate the threads that are going to go out of bounds is we have to make sure that the thread index is greater than or equal to the stride. So we can write, so over here we can write if thread index dot x is greater than or equal to stride, then we can do this access. And a very clear again, our rule of thumb is every memory access needs to have a boundary check. So here this buffer underscore s, right, to be able to access thread index dot x minus stride, thread index dot x minus stride needs to be greater than or equal to 0. In other words, thread index dot x needs to be greater than or equal to stride. Okay. Now, once we've done this, and what do we need to do in between each iteration?
Sync threads.
Right, exactly. I need to wait for all these threads to finish producing their output values before I move on to the next iteration where I'm going to use these output values. Okay, so I need to have a sync threads. Okay, and then once I'm done, we want to take this final output segment and we want to write it to our global memory. So we can do that. That's easy. We'll just do output of I is equal to buffer underscore s of thread index dot x. Now, one final thing we also need to do, which I told you, is the last thread needs to write the sum of the entire block to the global memory in order for us to be able to combine, to take that value and add it to the later blocks. So that's what the partial sums array here is for. So we're going to do that as follows. We're going to write if the thread that has this, the thread that owns this value is actually the last thread in the block this time. So if thread index.x is equal to block dim minus 1, and in this case, what we're going to do is we're going to write partial sums. The partial sums array is going to have
Partial
1
sums
and
of
2 for
block
each
index.
block. Exactly. So we're going to write partial sums of block index.x is equal to buffer underscore s of thread index dot x. Okay, so this is our scan implementation. Any questions?
Professor, shouldn't we sync after we read because we are writing directly after. We cannot guarantee that the threads don't continue to the new iteration. ولا ما دخل؟
Where do you mean we should sync? Are you talking about this one? Are you talking about this one? Or you think there should be
No.
another sync?
Shouldn't we sync after we write to the output array? Shouldn't we sync?
So you mean after we write to this output array, we should
No,
sync
تحت بعد
down
الأوتبوت
here?
هون.
Over here?
Yes.
No,
The
we're
block
reading.
isn't using the.
We're reading this value and we're also reading this value. We're not writing anywhere here.
Oh, okay. This is after we finish the.
Yeah.
Okay.
Yeah, but we should sync somewhere. I thought so maybe you were onto something. So let me compile and run and see what happens when we do this.
I think because sync thread is between the same block, right?
Yes, let's take a look. So I'm going to run this. Let me run this first. Okay. And we actually get an incorrect result. Okay. So we have a problem. There's a bug in our code and we need to fix this bug. So what's the bug? Some of you were saying that we need to sync. So where do we need to sync? Where do we have a missing sync? Let me go back to the slides. By the way, this is the code that we wrote. And we have something incorrect in our code, which is that we have different threads are reading and writing to the same buffer at the same time. So we have a race condition. And let me illustrate that to you. So let's take a look at the first iteration. In the first iteration, thread 1 is reading x0 and x1 and then writing. Remember, all of these are the same buffer, right? These are just different snapshots of the same buffer. So thread 1 is reading x0 and x1 and then writing their sum to the location where x1 previously was. But at the same time, thread 2 is reading x1 and x2 and then writing that result to the location where x2 previously was. So if we focus on x1, we see that thread 1 is reading x1 and then overwriting it. But then thread 2 is also reading x1. So what could happen is thread 1 could read x0 could read x1 and then write x0 plus x1 to that location before thread 2 reads x1. And if that happens, then what would happen is thread 2 will end up reading x0 plus x1 instead of reading just x1. Is this clear? If thread 1 reads x0, reads x1, adds them, and then writes the result of x0 plus x1 to this memory location before thread 2
Can't we
reads
solve this
x1,
with double buffering?
yes, so we'll get to that. You're right. We can solve it with double buffering, but let me first solve it another way. But yeah, you're absolutely right. So the problem here is that the same value is being read and written by multiple threads. Now, to solve this problem, what we need to do is we need to make sure that thread 2 reads x1 before thread 1 can overwrite x1. Is this clear? We need to make sure that thread 2 finishes reading x1 before thread 1 writes x1. And the way to do that is by letting thread 2 read x1 and then doing a sync threads and then letting everybody write their values. Is this clear? We let thread 2 read x1, we sync threads, and then we let everybody write their values. Okay? So let's see how to do that in the code. What we want to do is we want to make sure everybody reads, and then we want to do a sync threads, and then we let people go proceed and write. So let's
So we just
implement
use a
that.
temporary variable.
Yes, exactly. We can create a temporary variable. Oops, lost my cursor. There we go. Okay. So what we're going to do is we're going to create a temporary variable. I'm going to call it v. And we're going to do v equals, and I'm going to take this part right here that's reading, and we're going to put that in a temporary variable. Okay. And then we're going to sync threads. Okay. And then we are going
Shouldn't we
to
sync threads
write the value.
outside the if statement? Because
Yes, you're right.
this
So I cannot sync threads over here, correct? Why? Because not all the threads arrive here. Some threads are not active inside of this if statement. So this is also a bug. We cannot do that. So what we have to do is we have to close the if statement, do the sync threads when all the threads are active, and then reopen the if statement. And of course, to make sure that v is in scope over here and also in scope over here, what we're going to do is we have to declare v out here. Okay? So now what we're doing is we are reading the values, we're doing a sync threads, and then we write the values after we make sure that everybody has finished reading. Okay? This clear? Any questions? Okay, great. And so this is the code that we wrote. Okay, so the first sync threads in our code is making sure that we finish reading, right, before anybody writes. And the second sync threads here is making sure that we finish writing to the buffer before everybody reads. Is this clear? So let's compile this, run it, and make sure that it works. I'm going to compile it.
Professor, بس ليه الكود بالسلايدز different? We have
Oh, no,
one
it's just a
action
minor.
in the slide.
Yeah, I know. I did. There's a minor stylistic difference here. It's just a matter of style. Because here I'm doing buffer plus equals, whereas over there I did buffer equal buffer plus.
Okay, yeah, okay. Then
It's a
didn't pay
stylistic
attention to that.
difference. It doesn't affect the correct.
Professor,
Yes.
do we need to ensure that all the threads read before writing?
Your voice drifted. Could you say that again?
I was saying, do we need to ensure that all things?
Okay, so in the first iteration, right, you're asking, do you need to make sure that all threads need to wait to read before writing? I mean, if every thread is only going to be dependent on one other thread in the previous iteration, but it's actually very complicated for you to just wait for that particular thread. So usually it's easier to just do a sync threads than to have to just wait for an individual thread and synchronize with that individual thread. But you're right, every thread is only waiting for one of the other threads in the previous iteration. And that was the same for reduction, right? When we implemented reduction, it was the same thing. Every thread was only waiting for one of the previous threads. But we were doing async threads because it's simpler to do it that way. Okay, so I compiled, let me run. Okay, and as you can see, now our implementation is correct because we made sure that we got rid of that race condition. And also, this is the sequential CPU implementation, is 45 milliseconds. Of course, if you do it in parallel, the CPU will be faster, but you'll notice that the GPU is significantly faster. Here, the reason I have 3 kernels is because I have kernels that come, this is the kernel that we implemented that's doing a scan in each thread block. And then these are the later kernels that are combining the result across thread blocks, right? The one that takes the most time is the one that does the scan within each thread block, and you'll see that that's significantly faster than the CPU implementation. Okay, great. So now we have a working version of parallel scan, and now the question is, can we do better than that? Can we improve on this? Okay, this here is the code that we wrote.
First, most importantly, we have a double buffering situation.
Right,
We're reading
exactly.
and
So
writing to
some
the
of
same
you were previously pointed out, and now you're correctly pointing out that these 2 sync threads reminded you all of that double buffering optimization, right? So if you remember, we said that some sync threads are used to enforce true dependencies, and some of them are used to enforce false dependencies. Okay, let me switch the code we just implemented. So here we have 2 sync threads, which this sync threads is making sure that we finish reading before we overwrite with those values with new values. And this sync threads is making sure that we finish writing these values before we read them on the next iteration. So one of them is making sure we finish reading before we write. One of them is making sure we finish writing before we read. Which one of these is enforcing a false dependence and which one is enforcing a true dependence? Right. So somebody answered in the chat. The second one is a true dependence because we have to finish writing before we read on the next iteration. You can't read something before you've written it. But the first one is enforcing a false dependence because the only reason we have to finish reading before we write is that we are using the same buffer for reading and writing. Okay, so here our second sync thread enforces a true dependence, whereas the first one enforces a false dependence. How can we get rid of this false dependence?
Add a buffer.
Right, we can use two different buffers, one for the inputs into the iteration and another buffer for the outputs of that iteration. And that will look like this. So what we will do is we're going to have two buffers. We're going to load our input to buffer one. In the first iteration, we are going to execute that iteration and put the result in buffer two. Now, one thing to note is that when we do this, now the first thread is no longer completely inactive. The first thread actually does have a role to play. It needs to copy this value into buffer two. The value that doesn't get added, if I'm not adding anything, I still need to copy the value over so that it stays in my buffer. Now on the second iteration, buffer two is going to be my input. So here in the first iteration, buffer one is my input, buffer two is my output. On the second iteration, buffer two is going to be my input and buffer one becomes my output. And the iteration after that, buffer one becomes my input, buffer two is my output. And I keep swapping the buffers between the input and the output until I am done. Okay, is this clear? And again, importantly, now all threads are active every iteration because now every iteration, the threads that don't do any additions are still responsible for copying their value into the output buffer so that it can be used in the following iteration.
Isn't this true only for the first element? لأنه, for example, in buffer 2 in the first step, it's x0 to x1. Why does it have to copy to buffer 1? It's already being copied.
Yes, you're absolutely right. We can do the copy here and then not do it later. Over here, we can do this copy here and not do it later. And you can do that. It complicates the code a little bit, but it may or may not be worth it because you're just going to have divergence instead of a shared memory access. And to keep the code simple, I'm going to do the copy every iteration. But you're right. You can do some certain conditions to avoid that redundant copy every iteration. Okay. Any questions about this before we implement it? Okay, so let's go to the implementation now. So now, instead of having just this one buffer, okay, I'm going to have two buffers. Okay, I'm going to call them buffer one. So here I'm going to have two buffers. I'm going to call one of them buffer one and one of them buffer two. Okay, and then I'm going to create two pointers, an input buffer pointer and output buffer pointer that I'm going to use to keep swapping between the two buffers. So I'm going to have float star, I'm going to call this in buffer underscore s, and I'm going to initialize this to buffer one. And I'm going to have another buffer, I'm going to call that out buffer underscore s, I'm going to initialize that to buffer two. Okay? Now, at the very beginning, when I load from global memory, I'm going to load into my input buffer. Okay, so here, over here, I'm going to write in buffer underscore s is equal to input of I. Is this clear? Okay, now when I go into my loop, right, in each iteration, I'm going to read from the in buffer and I'm going to write to the output buffer. So here I'm going to read from the in buffer. So this is going to become in buffer underscore s of thread index.x plus in buffer underscore s of thread index.x minus stride. And when I write, I'm going to write to the output buffer. And because I'm reading from a different buffer than I'm writing to, okay, I no longer need to have the sync threads that makes sure I read before I write. So I can get rid of the sync threads. I can merge these two these two if statements. And now I no longer need to have this intermediate value. I can simply write out buffer underscore s is equal to in buffer underscore s of thread next dot x minus plus in buffer underscore s of thread next dot x minus stride. Okay. Now, of course, we said that the threads that are not going to do an addition have to do a copy. So down here, I'm going to write else out buffer underscore s of thread index dot x is equal to in buffer underscore s of thread index dot x. Okay. So by creating these two different buffers, I was able to get rid of the sync threads that was enforcing the false dependence and only keep the one that is enforcing the true dependence. Is this clear? Okay, great. There's a little more that we have to do. Remember, we have to swap the buffers each iteration. So in each iteration, the buffers trade places. So to do that, I'm going to swap the pointers between in buffer and out buffer. So I'm going to do a swap. So I'm going to create a temporary, assign that to in buffer underscore s. In buffer underscore s is equal to out buffer underscore s. And then out buffer underscore s is equal to the temporary. Okay. And now on the next iteration, after we're doing this, on the next iteration, the out buffer now becomes the in buffer. And we can read from it and we can recycle the old input buffer. It becomes the new output buffer. Is this clear? Okay, we also are using the buffer
Question.
down here. Yes?
Shouldn't only one thread do the swapping?
No, because every thread has a pointer to
Oh,
the
right.
swap.
Every thread has a pointer, yeah.
Right, so every thread needs to swap. This value is not shared. This value is a local variable. It's a local pointer. So every thread has its own copy of it. So every thread has to swap its own copy. So down here, when I'm writing the final result is going to be in which buffer? The input buffer or the output buffer?
The output buffer.
Are you sure?
50-50 chance.
It's the in buffer.
It's input.
It's going to be
Because
in
at
the
the end,
input
the in
buffer.
buffer.
Yes, go ahead.
You know, that's my answer. No input buffer. No, at
So
the end,
yes.
we're putting the value of the output buffer in the input buffer.
Yes, you're
We're
absolutely.
switching
So
them.
here we put the final result in the output buffer, but then we're swapping them. So at the end of each iteration, the value is in the input buffer. So here we're going to write in buffer, and then here we're going to use the in buffer. Okay, so this is how double buffering works. So before we introduce abstractly, I hope now you have a more concrete idea of how double buffering works. Let's compile and see the benefit that we got. So I'm going to compile, and I'm going to run. Okay, our result is correct. And now we've reduced our time from 0.39 milliseconds down to 0.303 milliseconds. So we got a 25% improvement in the execution time by getting rid of that false dependence. So you can see that the synchronization, the sync threads, does have a non-trivial overhead in these kinds of kernels that do a lot of synchronization. Okay, is this clear? Okay, great. And this here is the code that we just wrote. Okay, so as you can see, we got rid of the synchronization, but we're still synchronizing every iteration, right? So you can tell that in this code, probably the most expensive part of all of this is doing what? Is doing the synchronization and also doing these shared memory accesses. So what can we do to further improve, to further reduce the amount of synchronization that we do?
Thread coarsening?
We're going to look at thread coarsening, but we're going to look at next time. Before that, think of the
Warp-
last lecture. What did
warp
we do in the last
reduction.
lecture to reduce synchronization? Yes?
Warp reduction.
Right, we used warp level primitives. So last time, to avoid synchronizing every iteration, we used warp level primitives to do reductions at the warp level and then combine the result at the level of the entire block. And we can do something similar here, right? If we don't want to do a sync threads on every single iteration, one thing that we could do is we can decompose, we can use warp level primitives to decompose our scan across warps, have every warp do its own scan, and then combine the result. And let's see how we can do that. So we can further reduce synchronization with warp level primitives to avoid having to do a sync threads or a block-wide barrier synchronization every iteration. We can decompose our scan into segments across each warp. and you do a warp level scan using warp level primitives. And then after we have a scan segment for each warp, we consolidate the warp segments across blocks. So this looks something like this. Let's say I have this block segment right here that every block is scanning. What we could do instead is we can divide this block segment across warps, and we can have every warp do its own scan of the warp level segment without doing any barrier synchronizations. Okay, now we have a scan segment inside of each warp, but what we have to do is we have to consolidate these scan segments. So one way to consolidate the scan segment is, what I need to do is I need to add to the elements of warp 1 the sum of the elements in warp 0, which is this last value right here. We need to add to the elements in warp 2 the sum of the elements in warp 0 and warps 1, which is this value over here plus this value over here. We need to add to the elements in warp 3 the sum of the values in warp 1, warp 0, warp 1, and warp 2. So that's the sum of warp 1 plus the sum of warp 2 plus the sum of warp 3. So what does this look like?
The warp index times 32.
Well, that's the location of the.
That's just yeah, the location
but
of the
adding,
dependence. We're just
right, but adding
add
the
them.
right, exactly. But then adding warp 0 and warp 1 and warp 2 sums, what does that look like?
Reduction.
Well, it's a reduction, but for warp 2, I'm going to add the sums of warp 0 and warp 1. For
Scan.
warp 1,
Someone said scan.
right, it's a scan, right, you're right. Somebody mentioned in the chat, it's another scan, exactly. So what we're going to do is we're going to combine the sums of each warp. So every warp is going to contribute the sum of all its elements. Then I'm going to have one warp do a scan of the warp sums. So when I do a scan of the warp sums, this first element is going to be the sum of all the elements in warp 0. The second element is going to be the first sum plus the second sum. So it's going to be the sum of the elements in warp 0 and warp 1. The third element is going to be the sum of the elements in warp 0, warp 1, and warp 2, etc. So now I have the scanned warp sums. What each warp can do is it can go and get the scanned sum of all the previous warps and add that value to its own elements, and that will produce the final scanned block sum. So in other words, warp 1 goes and gets the sum of warp 0. Warp 2 goes and gets the sum of warp 1 and warp 0, which is this value right here. That value is the sum of warp 1 and warp 0. Warp 3 is going to get the scanned sum of warp 2, which is the sum of the elements in warp 2, warp 1, and warp 0. Okay, etc. So we do so every warp is going to do a scan. Every warp contributes its sum. We do a scan of the warp sums, and then every warp goes back and adds the previous warp's scan sum to its own elements to get the final result. Is this clear?
Professor, can you repeat?
Yes. So we start by having every warp scan its own segment. Now, once every warp scans its own segment, every warp still needs to add the sum of the elements before that warp to its own elements. Is that clear?
Yes.
Okay. So let's look at warp 2, for example. What warp 2 needs to add is it needs to add the sum of the elements in warp 1 and warp 0. Warp 3 needs to add the sum of the elements in warp 2, warp 1, and warp 0. So every warp needs to add the sum of the elements in the previous warp. So that's also a scan operation. So to get those sums, what we do is we have every warp contribute the sum of all of its elements into an array. We can put that in shared memory. Then we can have one warp scan those warp sums. So now what we have is the scanned warp sum. So each one of these elements represents the sum of all the elements in the previous warps. And then we can have every warp go back, get that scanned sum, and add it to its own elements so that we get the final result. Is this clear?
So basically we have the entire warps are working at first, and then we have a single warp do the sum of the warps, and then we take the sum of the warps and we use them on all of the the remaining warps to
Yes.
add the sums to them?
Yes, you're right. So here all the warps are active doing a scan. Then one warp is active scanning the partial sums. And then later all the warps except the first one are active. Each thread adds the scanned sum of the previous warp to all of its own elements.
Yes, it's clear now. Thank you.
Okay, great. Okay, so let's go ahead and implement this. One thing to note here, because the whole point of this was reducing various synchronizations. How many various synchronizations do I need for this whole process?
1.
Not just one, I need 2. Okay, so here when I do the warp scans, I don't need a barrier. But then over here, when every warp writes its value to the shared memory so that the first warp can do the scan, right? We need to sync threads so that the first warp makes sure that all the previous warps finish writing their values before it does a scan. And then after this warp finishes doing the scan, we need to do another sync to make sure that all the other warps wait for it to finish scanning before they do their add. Okay? So we, instead of synchronizing every iteration by using warp level primitives, we only synchronize twice. Once in between the individual warp scans, the scanning the partial sums, and once to finish scanning the partial sums before we go back and do the additions. Okay, great. Let's implement all of this. Okay, I'm going to start. So first, I'm going to define 2 functions that are going to help me out. I should have done this last time, but I didn't. I was a little lazy. But this time, because we're going to use them a lot, I'm going to define them. So I'm going to define 2 functions. One function that calculates the index of the warp. So I'm going to call that warp index. And if I have my thread index, how do I calculate my warp index?
Over 32.
Right, I divide by
Much.
the warp size. I'm going to define a macro. I'm going to call it warp size and thread index.x divided by the warp size. This way, threads 0 to 32 are going to have a warp index of 0. Threads 0 to 31, threads 32 to 63 are going to have a warp index of 1, etc. Another thing I'm going to define is the index of the thread within the warp, and we call that the lane. Okay, so we're going to call that the lane index. So the lane index is the index of a thread within the warp, and this terminology comes from SIMD lanes. So how do I get the index of the thread within the warp?
Thread index modulo warp size.
Right, I'm going to do thread index.x modulo the warp size. Okay, so this gives us the warp index and the lane index. Great. So now let's go and implement our scan operation. So first, I'm going to implement a function that does a warp level scan. Okay, how do I do that? I'm going to declare a device function. I'm going to call it warp scan. It takes a value. And what we're going to do is we're going to do a scan. The scan is going to be very similar to this scan right here. Okay, so we're going to loop from stride equals 1 up until, but this time we're not going to go until block dim over 2. We're going to go until, what is the size of our segment in this case?
Warp size over 2.
Right, exactly. We're going to go to warp size over 2. And then in each iteration, what we're going to do is we're going to have, we want to get the value that is stride to the left. So what are we going to use? Shuffle up or shuffle down?
Shuffle down, no?
So we're gonna shuffle every thread wants to get the value that is stride to its left. So we're gonna
We
shuffle
shuffle
from
up.
the lower ID to the higher ID, right? So we're going to do what?
We shuffle up.
Shuffle up, exactly. So I'm gonna call this the left value. That's the value that's stride to my left. I'm gonna shuffle it. I'm gonna do shuffle up, sync. I'm just gonna provide a mask that indicates that all the threads are active. What's the value that I'm shuffling? It's val, right? The value that I passed. And how much am I shuffling? I'm shuffling it by stride. Okay, so this over here is going to shuffle the value from the left, from the thread that is stride to our left up until the current thread. Of course, the threads that are shuffling from a stride that takes it out of bounds are just not going to do anything. Okay, now what I want to do is I want to, so let me ask you, what is val? Val is this variable that I passed. It's the parameter, and I'm also going to use it as the, to kind of evolve the value of that I'm writing. So here, what I want to do next, after I shuffle the left value, is I want to do val plus equals left val, right? So every thread is going to take its value and add to it the value that it shuffled from the left, right? But are all threads going to do this?
Only the ones whose lane is greater than or equal to stride.
Right, exactly. Because the ones whose lane is not greater than or equal to the stride will have shuffled a garbage value. Okay? So just like over here in the previous case, we have if thread index.x is greater than or equal to stride. Over here, we're going to have if the index is greater than or equal to the stride. In this case, our index is what? It's the lane index. So I'm going to do if lane index is greater than or equal to stride. Clear?
Professor, the condition is wrong.
Index.
Thanks. Okay, so now I'm done with the warp level scan. And of course, at the end, I'm just going to return the value. So here I did the iterations to do the warp level scan. Great. Now let's implement a block level scan. So I'm going to define another device function. I'm going to call it block scan. And here, every thread in the block is going to pass a parameter. I'm going to also call that val. Okay. So in the block scan, what's the first thing that we do? The first thing that we do in the block scan is every warp is going to do its own scan. So now you can think of this block segment as already being loaded into this val, and every thread is passing val as a register. Okay? So first, every warp is going to do a scan of its values, right? So the first step is I do the warp level scan. Okay, so I just do val is equal to warp scan of val. So when I do val equals warp scan of val, now every thread took, every warp took its input segment, which is across the registers of the threads, and scanned it, and now I have these scanned warp segments. Is this clear? So I finish, so this line right here, val equals warp scan val, does this first step. Okay, next what I need to do is I need to have every warp put its sum inside of a shared memory array for warp 0 to scan them. Okay, so I need to declare this shared memory array. So I'm going to declare a shared memory array. So here I'm going to collect warp sums in the shared memory. So I'm going to declare a shared memory array. Oops. Let me call that warp sums underscore s. How big should it be? Well, it should be 1024 divided by 32, which conveniently happens to be 32. Okay, so it's going to be block size over the warp size, which is 32. And then we're going to have every thread, every warp, the last thread in the warp has the sum of that warp. So that last thread is going to write that value to the shared memory array at the warp index, right? So what's the last thread of the warp? It's the thread whose lane index is what?
Warp size minus 1.
Exactly. So warp size minus 1. So the last thread in the warp is going to do what? It's going to write to warp sums underscore s at what index? At the warp index, right? So the thread in warp 0 writes the index 0. The thread in warp 1 writes the index 1. What's it going to write? It's going to write its val, which is the sum. Okay? So now by doing this, what I've done is I've written the sums into the shared memory. Of course, after I do this, I need to sync threads to make sure that the first warp somebody's do I have a typo somewhere? Somebody, right, it's block dim, not block size. Excuse me. Okay, so now I've collected them in shared memory. The next step is to do what? Well, the next step is for warp 0 to do a warp scan of these warp sums. Okay, so here I have the this is my second warp scan, and in this case only warp 0 is going to work. So I do if warp index is equal to 0. This ensures that only warp 0 is going to do this scan. And what does warp 0 do? It's going to load these values, do a warp scan, and then put them back in the shared memory. So I can do warp sums underscore s of lane index is equal to warp scan warp sums underscore s of lane index. Is this clear? So every warp is going to get one value from the warp sums. Okay, it's going to do a warp scan on that value, and then it's going to put the result back in the warp sums. Okay, now one thing to note here is that here I'm making the assumption that the number of warps I have is equal to the warp size, which is the case. Number of warp sums is 32. Number of warps is 32, and the warp size is 32. Okay, if this wasn't the case, I would need to have a boundary check when I'm loading from here and a boundary check when I'm storing to here. I'm not going to worry about that boundary check. Okay, because conveniently the number of warps and the size of the warp are the same. Okay, great. So now that I've done that, I need to sync threads again to make sure that all the other warps, wait for warp 0 to finish doing the scan before they do their add. Okay, now that I'm done with the scan, the final step is to do the add. So in the add, all the warps except warp 0 are going to do an add because warp 0 already has its values complete. So here I'm going to do if warp index is greater than 0. Okay, so in this case, every thread is going to do what? It needs to add to its value the sum, the scan sum of the previous warp. So every value, it's going to add to it the warp sum of the previous warp. That's going to be warp index minus 1. And here, because I did warp index is greater than 0, this ensures that warp index minus 1 is not going to be negative. Okay? And then after doing this, now I have all the final block segments inside of val. Now I can return val. I know I'm a little over time, but I just need 1 more minute. I'm almost there. Okay, so now this code right here does the block scan based on what I just described right here. Now that we have a block scan, the rest of this is easy. I don't need any of this anymore, right? All that double buffering was just to teach you how to do double buffering, but I don't need that anymore. What we can do now is we can simply every thread is going to load the input value from input of I. We're going to call the block scan function, which is going to return the scan value for each block. And then in my output, I'm going to write the result of the block scan function. And of course, the last thread in the block is also going to write that as the partial sum. Okay, is this clear? Any questions about this? Okay, so let's compile and run. Let's make sure let's hope we don't have any bugs. Okay, so before my time was 0.3 milliseconds, and now after using the warp level primitives to get rid of the synchronizations, our result is correct, and we're down to around 0.21 milliseconds. So again, you can see that when your code is no longer doing a lot of arithmetic, and when your code is no longer doing a lot of global memory access, we just load from global memory at the beginning, and the rest of it is using shared memory. The shared memory and the sync threads all of a sudden does become a significant part of the execution time. So these optimizations that we're covering of using double buffering and of using warp level primitives are important in order for us to get rid of the overhead and improve the performance. Okay. So this here is the code that we wrote today. Does anybody have any final questions before we end? Okay, if there are no final questions, then that's all for today. And next time we'll continue looking at more optimizations for prefix sum, for scan, and also we'll look at how to consolidate the result of the scan across many thread blocks. Okay, bye everyone.
Thank you, Doctor.
Thank you.